Okay, today we're gonna, in the next few classes, we're gonna be spending some time just exploring some examples of using this event graph methodology to model various different situations. A lot of these, at least at first, are gonna be various tweaks or modifications of our basic queuing model. So today, I'm going to look at one variant of that, where we have a situation where we have two servers, and then in what I think is the final piece of the methodology, where we'll look at the use of containers. And I think after this, there's going to be only one more piece of the methodology, which is going to involve explicit things called entities. But all that is forthcoming. So what we notice in our system here, and again, with the iterative approach that I've been ranting about a little bit, we start with a simple model, and then what we notice is that one of the assumptions that we were making in our multiple server queue model was not met in this particular situation. And in this particular situation, there are two types of servers. So in the multiple server queue, there's only one type of server. They're homogeneous, not in the sense that they always give exactly the same service time, but they have the same distribution of service time. But here we notice that there are two different types of servers. Like one use case of this is, say, a fabrication shop where you have machines that perform one particular type of function, and you have two different types of machines that perform the same function. In situations I'm familiar with, a lot of times you have a set of older models and newer models, and so you always want to prefer the shiny newer model because it might be faster or cleaner or for whatever reason. But if there are jobs to be done, you never want to be in a situation where you have an available machine and it's just sort of sitting there idle. Okay, so the idea is that the customers are all basically the same still, but there are these two different types of servers, and the customers kind of know that. And again, by customers in this use case that I'm describing, which job would go on which machine would be something that some guy would decide. So it may not be in this case, the jobs are these physical things and they don't have any preferences, but the guy who's doing them has a preference. And the preference is that for whatever reason, the type 0 server, we'll call them type 0, you can call them whatever you want, but the type 0 servers are going to be preferred over type 1 servers. So what is that? What are the implications of that in the model? So the idea is that if a customer comes in, then if there's a type 0 server available, they will go to that. But if they're all busy, then they'll go to a type 1 server. So in other words, if all the fast and shiny new machines are working and you have another part that needs processing and you have available of the slow and clunky ones, then you still put it on the slow and clunky ones instead of just letting it sit there. Because if that were the situation, then there would be no purpose of having these other slower ones. And generally speaking, I guess as one guy once told me, he said if my machines aren't cutting metal, I'm not making any money. So basically, if you have tasks to be done and the facility to do it, then you want to do it even if it's not the preferred one. Okay, So you see that right off the bat, the multiple server queue model that we've been looking at doesn't fit this. Because there, the assumption was that all the servers were homogeneous. Okay, so how can we capture this? Well, right off the bat, we have parameters that are, we need two sets of parameters. So we need, and kind of motivated by the multiple server queue, we have a certain number of the type 0 servers and a certain number of the type 1 servers. And what is it that distinguishes them apart from the label is typically the service time. In other words, presumably you would prefer the faster server, but it might be that there might be other circumstances. In other words, the preferred server might actually be a little slower but more reliable. Now we're not capturing things like a failed service here, which again in a machine shop definitely happens. So, and we're not capturing that, but we could, and that might be an exercise for the interested reader to capture that piece. So it may be speed, it may be reliability, it may be a bunch of other factors that cause us to prefer one or the other. But regardless, the service times are going to be different, and we need to explicitly model that with a. Okay, so right off the bat, we have a different situation. Now, motivated a little bit by this componentization that we've been doing, you notice that we're not going to explicitly model the arrivals here until the very end. And so with an arrival process in our pocket, we can say, well, whatever the arrivals are going to be, we will handle that using an arrival process and then use the sim event listener concept to connect them to this. For certain models, we may need to tweak that a little bit, and we've seen an example of that with the transfer line, where the arrival process just out of the box was not sufficient. We just had to tweak it a little bit so that it produced an arrival event with an argument that was an integer. So, but if you remember, that was a very, very lightweight type of thing, very easy, very straightforward. Okay, now state variables. Again, now, since we only have one type of job, one type of customer, we only need a scalar for the customers in the queue, the number of customers. But now we need two different state variables for the number of available servers of either type 1 or type 0. And the reason for that is if we only had one state variable, which is just the number of available servers, and a customer shows up, and you need to say, okay, well, which type of server is it going to go to? Is it going to be processed by? And I only know that there are 3 available servers. I don't know what kind they are. Okay, so in other words, if you then encounter a situation where there are more than these types, then you need to have state variables that explicitly take those into account. We saw that in the tandem queue. We saw that in the transfer line, where the things like the number in the queue and the number of available machines or servers was, in those cases, arrays. I mean, here it kind of looks array-ish, but there are only 2 of them. We're just doing the 2 thing. Okay, so we've done the first 2 steps in creating our event graph model. We've defined our parameters, and again, how do you know when you're done? In a sense, you're never really done, because there's always kind of more stuff. But at some point, it becomes good enough for government work, as they say. So we have our parameters, we have our state variables, and now the next step is to look at our events. So, and I'm going to do that by hand for you, just again to emphasize the fact that I want to emphasize the fact that even though we've done a bunch of these, the tendency I've noticed a lot of times is to just kind of start drawing the whole thing from the beginning. And what I'm really trying to emphasize here is that it is a better path, in my experience, to get a model that's functioning correctly if you follow this path. In other words, what we are now going to do is try to identify the state transitions and identify with those as events. And we always start with the run event. And we start with that because it helps us overcome the blank sheet of paper problem. And if we have defined our state variables completely, including their initial values, then we can always write something down like this. And in the case of arrays, and we'll, actually I think after doing this, I'm going to redo this using arrays as well. But for right now, we're just going to stick with scalars. But if they're arrays, then we have that init for loop type of deal. So if you remember, my recommended approach is to pick a state variable and then ask yourself, what is it that could cause that state variable to change? So if we pick Q, then we have our friend, the arrival. We've called it arrival, but you don't have to, you can call it whatever you want. It's not the name that causes it to do something. It's this state transition that causes this event to be something. Just like the name of a method in any program does not specify what that method does. It's the code in the method that makes it do. So, I mean, it's like supposedly it's probably apocryphal, but supposedly they asked Lincoln at one point, if you call a tail a leg, how many legs does a dog have?
Still has 4.
Still has 4, because calling a tail a leg doesn't make it a leg. So likewise, just calling this an arrival doesn't make it an arrival. Saying that now there's one more in the queue is what makes it, quote, what we're calling an arrival. And then, okay, what else could cause it to change? Well, it could start service on either, let's say it could start service on its preferred server. Okay, so and I'm going to say start service on the 0th one, or it could start service on the other one, the unpreferred one. And we don't know which one is going to be, and this is why you want to do them one at a time and just kind of check your work, as it were. Okay, because and again, I'm a real baby about this and doing things one step at a time, because when I don't, I find that it's just easy. It's just even with something as simple as this, it's easy to make a little mistake like that. And it's easy enough to make a mistake when I'm translating this into code. Okay, those are the only ones that I can think of. But now let's look at, say, the number of available servers of type 0. What could cause that to change? Well, if we start service on a server of type 0, that will cause the number of available servers of type 0 to decrease by 1. And another thing I hope you've maybe noticed, but I want to point out right now, is that every every piece of the model should be explained in plain English. And if you can't do that, then maybe there's something amiss with the model. In other words, as far as the model is kind of doing this. Just like in a program, it's the code that does what it does. But if you have code and you're trying to explain it to your client, as it were, the person that you're writing the program for, and you can't explain it in plain English so that they understand it, then you should take a step back and say, okay, what the hell am I doing here? So in plain English, the start service 0 event corresponds to beginning service for a customer on a server of type 0. And the on server of type 0 is kind of the key part, because that's what is reflected in the model. This state transition is what happens. And what else could cause this to change? Well, we could end service. I mean, we're calling it end service, but again, you don't have to call it anything. These names are not magical or laws of nature. But what causes the number of available servers of type 0 to change is when they complete service on any kind of part. And since the parts are all the same, then we don't have to kind of, again, we've already taken into account all of the possible state changes for the state variable number in the queue. We've now taken into account all the state transitions for the number of available servers of type 0. And then now what about type 1? Well, for type 1, again, it's kind of the same thing. And then if we're kind of done, then we can put the little, just, why, this, the guy who invented these liked to put curly braces around the state transitions. So if you don't put the curly braces, you're not going to get marked down. But it but, I mean, I learned this from the guy who invented them, so I genuflect in his direction every time I do this. So. Okay, so and then the question to be asked is, are we done? How do you know you're done? Well, you're never 100% sure. But in this particular case, I can't think of any additional state transitions that could happen. Okay? That doesn't mean that they don't exist. It means I can't think of them. Okay, but now we proceed, and again, remember, notice we're not modeling the arrivals here because we're going to assume that this is going to be listening to some arrival process off somewhere that's going to trigger these. And when it hears the arrivals, it'll kind of kick things off. Okay, so now the order that you do these, you don't necessarily go left to right or anything. There's no order to this. So I'm going to start here because the start service on 0 event, what events did that schedule? That's the question you asked. When this event occurs, what other events would it schedule? In this particular case, it would only schedule an end service event on server of type 0, and the delay is going to be the service time for type 0. And similarly for type 1. And are there any other events that start service 0 would schedule? I can't think of any. Again, that doesn't mean there aren't any, it just means I can't think of them. Okay, so now, what about the end service event of a server of type 0? Well, again, motivated by our multiple server queue, that might schedule a start service event if there's somebody, oops, no, there's no Q0. If there's somebody in the queue and we finish service, we can schedule another start service event. And similarly for the end service one here. Now we have to be a little bit circumspect here because here's some thinking that may or may not, well, it's useful to kind of think of this, but it's also useful to come to the right conclusion about it. So when we finish service on a server of type 0, do we need to worry about what the state of the other server is? In other words, well, in a more practical sense, do we need to maybe schedule one of these events? Like, do we need to schedule a start service 1 when we have an end service of type 0? That's a question that ought to be asked. So what's the answer? You're right. Now, why not?
Because all that customer at the second server is worried about is just having the service and then he's done.
Right, yeah, you're absolutely right. That's what the customers worry about. What about the server?
He's just worried about the arrival.
Yeah, he's only worried about who's in the queue. Yeah, so yes, so the answer is correct and the reasoning is correct. It's always good to have. But that's something that in certain circumstances we may have to worry about. In other words, in some circumstances we may have to check and see whether other events could be scheduled. And in fact, that's going to come up right here. So when an arrival event occurs, what is an event that it might schedule? Okay, wait, no, we have 2 start service events. Which one?
Depends on which one
If
is
he has,
service he has a
Yeah.
customer.
if he has no preference, then service 1, I guess.
Okay, so if there's a now, kind of motivated by our multiple server queue, we could say, well, if there's a server of type 0 available, we'll schedule a start service 0. And again, motivated by the same thing, we are certainly tempted to do this as well. Okay, so if there's an available server of type 0, we'll schedule a start service of type 0. If there's a server of type 1 available, we'll schedule a start service of type 1. Which, again, if we're just kind of going from the multiple server queue, this kind of makes sense. Now what I want to ask you to do here is now, what will this do? As it sits right now, what will this do?
Schedule 2 services.
Exactly. It will schedule, if both a server of type 0 and a server of type 1 are available, it will schedule start service event. In other words, the customer shows up and they go to service in 2 different places. That's what this model does. And again, like there's no, I mean, even NetBeans won't flag anything like this, because if this is done syntactically correct, then there's no, syntactic error.
Couldn't you just expand that by adding another condition to the transition, like for is F0 is greater than 0, and of the bottom one can be S1 is greater than 0 and S0 is less than 1.
Yeah, exactly. In fact, that's exactly what or say or less than 1 equals 0, same thing. Yeah, that's exactly what, and the reason why that's correct is it gets back to our priority. Now, you have to kind of, this is not the same as the event priorities we were talking about the other day. This says that when an arrival event occurs, the server of type 0 is preferred, But they will start service on a type 1 if it's available. So if it's available, yeah, if a server of type 0 is not available. So the key here is that this piece is what embodies the criterion that if the server of type 0 is not available. So this says the server of type 1 is available. This says the server of type 0 is not available. So that's what that's what you need. Okay, so now everything up until here was more or less just exactly the same as the multiple server queue, but you have to be really careful, and this is why it's important to kind of do things step by step, because things like this will come up. Okay, and basically, let's see if I did it right. Yeah. Okay, now you can do the same thing with arguments. And I'll circle back to this, and if I don't get to it today, we'll talk about it tomorrow. So, the fact that we have sort of S0, S1, K0, K1, etc., suggests that we could do this using arrays, and indeed we can. And so if you're actually the guy who invented these event graphs, Lee Shruma was his name, one of the things he was concerned about was identifying places where we could reduce the number of events. And so for him, kind of cutting down the number of, here we have like 5 events in addition to run. Here we basically have, the run and init are just kind of, they don't necessarily, count as much. But here, our start service and end service events, we can turn into events with arguments. And we just need to be a little careful about how we do that. So the thing here is that when we basically one way of looking at it is when we collapse the start service events and put an argument on it, first we need to make sure that we pass the argument. So from start service to end service, we've done something very similar to this in the transfer line. So when we start service on a server of type I, we'll end service on a server of type I, but we have to pass it the I. And the service time is also with I, and the state transition is based on I. And how does the event know which I is? You tell it, you pass it. That's why the boxes are there. The run event now has to use this init, although you could still get around that a little bit. But the other key difference here is that now the arrival event has 2 scheduling edges into start service. One where it's passing 0, and it has exactly the same criteria as before. S0 is bigger than 0, we say we start service on a server of type 0. But if S0 is 0, that is if there are no of the preferred servers available and there's a server of type 1 available, then we schedule start service passing it a 1. And so the other conclusion that you could draw from this is, notice that we have 2 scheduling edges that schedule the same event. So that is absolutely legal. You generally want to do that only when you have, this is the syntactic equivalent of an if-else if. So if S is bigger than 0, else if S1 is bigger than 0, and because it's an else if they're both 0, then you do nothing. Now how do we get this to work? Again, as it sits by itself, this component and this component will just execute the run event and then do nothing. So in order to get it to work, either one, we connect it as a sim event listener to an arrival process, and the arrival events will trigger, if we use this model, this component, it will trigger this arrival, and if we use this one, it'll trigger this arrival. And then once that event gets heard, then it will continue on its way. As we've seen with the multiple server queue, and as you have undoubtedly seen by this point in the computer assignment, where you took your arrival process and you connected it to this server component that didn't have self-scheduling arrivals, hopefully. Okay, is that fairly clear? Okay, containers. Now, it turns out that containers are a very useful way of modeling certain state variables. So, and event graphs are going to allow that. So one issue with our multiple server queue, as we've seen so far, is that it cannot explicitly give us things like the expected delay in the queue or the expected time in the system. And that is because our state variables, Q and S, were simply the accounts of them. And as you saw in that first written assignment, there are situations where if we have more than one server, customers can pass each other. So if we have a single server queue, then the customers come out, the whole system is first in, first out if there's just one server. But as soon as you have two servers, then it is not the system is not first in, first out. The queue can be first in, first out, but the system is not. In other words, customers can pass each other, and what that means, if you remember, in order to compute things like the delay in the queue, you had to go back over the whole sequence of events, figure out, okay, the customer came in here and started service here. They came in, they stay here, and then there was one guy who just had a ridiculously long service time, and so his arrival and end service were not in the same order. So you had to comb through the whole sequence of events in order to do that, and that's not something which is a reasonable thing to do, and it's certainly not something that can be done in the multiple server queue, just as it sits. Now, in many situations, Little's formula kind of rides to the rescue in the sense that it holds exactly in certain circumstances, and it holds approximately if we run it long enough. And depending on the particular application, we will often be running our model for a long, long time to reach some kind of steady state condition. In that case, Little's formula will typically hold. Part of the problem there is that is a challenge to brief someone. So if we're somehow briefing someone and they're interested in, say, the time, what is the lead time for this? What is the time between when the things come in and when they come out? And then we start waving our hands about Little's formula, and if they've never had this class or a class where they've encountered that, then it becomes a bit of a problem to try to brief. I mean, it's something which Little's formula is, in fact, very true, but that doesn't make it easy to brief. Much easier to brief would be a model which explicitly tallied those things. And so that's now what we need, and that's how these containers can be very useful. So one step in that direction. Ultimately, what we are going to do is we're going to create objects called entities. But if all we want to do is tally the customer times, then what we can do is have a container of the arrival times. In other words, if you remember, how did you compute those delays in the queue and the times in the system? Well, you needed to know what the arrival times were. And if you knew what the arrival times were, then you would be able to determine what they are. So how can we know what the arrival times are? The state variable Q, the capital Q, remember, if Q is just the number in the servers, that does not have the information that we need. What we need is the key and piece of information is when did each customer arrive? And if we have 10 customers in the system, we need 10 different things.
Can you just record the time at which property acquired a property?
You can, except that because the system is not first in and first out, you don't know exactly which one is which. So the key here is that we need to know what those arrival times are for each customer, so that when a customer, let's say, finishes service, then we need to know what time did they arrive. That's what we need. And to do that, we need to have as many of these times as there are customers. So for some reason, it just makes my mouse disappear. Now you're going to change my color, UCR, aren't you? Okay. So now, same parameters as before. We're not going to model the inter-arrival times because we got our arrival process. So we have our friend S, the number of available servers. We don't need to change that, but now we're going to have a container of arrival times, and its initial value is going to be empty. Now, in order to compute these delays in queue and times in system, we're going to do what you suggested, which is we're going to fire the property changes when they occur. The thing is, now we're going to fire the property change of these values. So one is going to be the delay in the queue, the other is the time in the system. And now notice that their initial values are now NAN. Why? Well, because when the system starts up, we do have K available servers. Our queue is empty. But what is the delay in the queue before we've even had a single delay in the queue? Meaningless. I mean, so we started up our system. What's the delay in the queue? Nobody's delayed yet, so it's just not there. And there, what that leads us to is the difference between. This thing disappears again. Time varying and tally. So, S is a time varying state, as we've seen, and in the written assignment we computed as such. In your computer assignment, you're estimating the means using a time varying stat object. Now, the container queue is also time varying, but its value is really its contents. And typically for that, if we want to do something like what is the expected number in the queue, then it's just kind of the size of it that's a state variable. And there's a stat object that handles that. But the delay in the queue, D, and the time in the system, W, those are tally state variables, because if you remember, when you computed those, you added them up and divided by the number, the normal means. So those are going to be a little bit different. So our events are going to be pretty much the same or similar as what we had before, except, why does it keep making my thing disappear? Okay, so let's look at this. So now our arrival, now instead, there is, before we just added one to queue. Now what we're going to do is we're going to add the sim time into our container. That's what the arrival event is going to do. And in terms of the size of the container, that does the same thing. But see now we can't do that with our old capital Q because that was just an integer. This is a container, and so now we simply add. When we say add to it, we're not. We're taking the value of sim time and we're just putting it into this container. Now let's look at the start service event. So one way of, at the start service event, that's where we can compute our delay in the queue, and that's how you did it by hand. So how do we do that? Well, we can pop off the first time, and that is the time at which that customer arrived. So when they showed up, it's like think of a parking garage. So in the parking garage, you go, you get a ticket. It's stamped with the time that you showed up, and then when you leave, you show them the ticket. They stamp it again, and they subtract them. And that's basically what we're doing here. We pop off the first one, and again, if we're implementing this, depending on the language, the exact terminology we would use might be slightly different. So in Java, we'd have to kind of do a little dance around this, and we'll see that at some point. But now, what's the delay in the queue? The delay in the queue is the difference between the current sim time, what time is it now, and when that customer showed up. And that's the delay in the queue. And then because we are conceptually firing a property change when that happens, that's all we need to do. So when that delay in the queue occurs, and we will fire that property change and then assume that there's going to be some statistics object listening for that, and that's going to be what in SimKit is called a simple stats tally, and that will simply tally those results as they come in one at a time. Now, because the queue itself is first in, first out, we can get away with just popping it off. But we can't get away with that when we're looking at the time in the system. So that when we have an end service event, we need to tell it what is the time at which the customer for who is ending service, when did they show up? When did they arrive? So we're going to pass that value to our end service event as an argument. So that the time in the system is going to be the difference between what time the end service event occurred and when that customer showed up. Does that make sense? And so in terms of scheduling, again, we have the same criterion here. If there's an available server, we can schedule a start service. Our start service event schedules an end service with a delay of a service time, but then it passes this local variable t that it popped off the queue. It passes that to end service so that when end service occurs, the time in the system is the one for that customer. And so the order in which these happen is irrelevant. In other words, this is when, again, this is basically like when you're exiting the parking garage. It doesn't matter whether there were other cars that kind of are still there. In other words, this end service event will occur in an order which is not first in, first out, based on the customer arrivals, but it will occur with the correct arrival time of the corresponding customer. And so for event graphs, all we need to do is basically compute the state variable and express it here on the event graph, and it will be in the implementation. It will fire a property change, and then some stats object will hear it. And you might be wondering why do things that way. It's because the key element here is to separate computing the statistics from the dynamics of the model. So the event graph model is what defines how the model dynamics work. But the statistics you're interested in are going to be typically some subset of the things that you could compute from this. And Murphy's Law says if you embed the statistics into the model, then there will come a time when you want some other statistic that you've forgotten to put in. And then what do you do? There are two cases. One is you have access to the source code, in which case you have to go in and edit a component that you've already verified, and so now you have to re-verify it. So then just like surgery, there's no such thing as a trivial edit once you have a verified component. Or if you don't have access to the source code, then you're screwed. And that's the, I have had students in the past who have worked with off-the-shelf models, and you know, again, being you know, because you guys are so creative and thoughtful and push the envelope, you know, he said, well, what if we tried to look at these statistics for this model? And it turned out that he couldn't. Why? Because the people who wrote the model had all the statistics embedded in it, and they hadn't bothered to ask the questions that he was asking. So had to do something else. That will never be the case in this framework. Because any metric, any measure that you have that's possible to extract from this or any model like this is always going to be some function of the state trajectories of that model. And if every state transition is firing a property change, then you can compute anything that's possible from this model. So if they had designed this model in the way that's done here, then it would have been possible to do what he wanted. Okay, so any questions?
So essentially what you're saying is the off-the-shelf model just didn't have the right connections in order to go back and change it, or you didn't have to.
Yeah, no, I mean, in an off-the-shelf model, you're not going to have access to doing it. You can run the model, and that's about it.
And that's the primary